While optimizing a splice mode can technically be done without a specific user interface, AFL's FPS program is incredibly helpful for tracking, recording, and interpreting splice results. Using a combination of FPS's power meter feedback module and data collection module, it's easy to keep track of how your splice results change as you make parameter adjustments. Before getting started though, let's review the workflow steps for optimizing a splice mode. First, you'll look for an existing recipe as a starting point. Next, you'll optimize the splice mode parameters to achieve the best loss and reliability. And after that, you'll optimize the estimation settings. And finally, you'll verify the optimized recipe. So first, it's helpful to identify a recipe to be used as a starting point for your splice. It's okay if you can't find one or if one isn't available, but it's helpful to have a predefined starting point. Take a good look at your fiber specifications and compare them to the parameters listed in different modes of the splicer. If there's a splice mode with similar parameters to your splice combination, use that mode as your starting point. If you can't find anything that's similar enough to be useful or have questions about your fiber combination, don't hesitate to reach out to us and ask for help. After identifying your starting point, we can get started optimizing the splice parameters. I'll revisit the information laid out in the previous video and start with entering my basic fiber information, then move through the splicer setup and fiber preparation. For the sake of time, I've already done this, but you can refer to the previous video for a more in-depth, detailed explanation. After that, I'll choose my alignment methods based on the fibers I have and begin adjusting the splice mode parameters. I'll start by selecting my arc calibration method and performing the arc calibration. For the single mode fibers I have here, I'll be using the standard arc calibration. Next, I'll optimize fusion time and power, followed by the prefusion time and prefusion power. If necessary, after this point, I can optimize the gap, overlap, electrode gap, and other splicing related settings as I move down the list. During the process, I've made sure to record data from each splice. This will serve as the data set for optimizing the loss estimation. So, to get started, I'll fire an initial 1.5 second arc, wait for the splice to finish, and estimate while watching the loss value. Then start firing my re-arcs. My particular fiber combination here is quite simple for illustration purposes, but the process is identical for any other fiber combination. A short initial splice followed by a series of 1 second re-arcs, watching the splice loss reach a minimum and then climb away from the minimum. At this point, multiply the total re-arc time by 0.7 and add the initial arc time to calculate your ideal splicing time. At this point, I'll move on to the prefusion parameters. These should be relatively close from the start since they're a function of the calibrated arc power, but a prefuse cycle that is too far off will show defects in the finished splice image. If the prefuse doesn't provide enough heating, this will result in a splice that typically shows the cores rippling from the overstuffing or underheating condition. A prefuse that is too hot or too long will usually result in a thin splice or fibers that fail to fuse together. After tuning in the prefuse, we can move on to the rest of the splice parameters, but the three key parameters to investigate here are the electrode gap, the fiber gap, and the overlap. As mentioned in a previous video, the electrode gap is primarily a function of the fiber's cladding diameter. So at this point in the optimization, you can tune in the electrode gap if it makes sense to change the size of the heating zone. Keep in mind though, that this will reset the arc calibration's accuracy and require you to use the special arc calibration method. After choosing an electrode gap, fine-tune the fiber gap. If the prefuse power and time adjustment doesn't seem to help with insertion loss, it may be helpful to widen the gap between the fibers. This can be seen mostly in the gap used with larger fiber splices compared to smaller fiber splices. Typically, a 125 micron fiber uses a gap of 10 to 15 microns, where by contrast, a 400 micron clad fiber typically uses a gap size of about 75 microns. Similar to what I mentioned earlier regarding the prefuse time and power, the overlap amount plays a direct role in the fibers melting together. Too much overlap can function the same way that an insufficient prefused power or prefused time does, meaning that the splice was pushed together too much for how much the glass was melted or softened. In this case, the image will usually show the characteristic rippling artifact that's seen with underheated glass. So now that our primary splice mode parameters are pretty well dialed in, let's take a break for a bit to talk about splice image analysis before going over loss estimation. Along with the numerical data captured in FPS are the splice images. While more difficult to interpret, these images can hold some key information about the fiber's behavior at the splice point and point to potential solutions or restrictions that will improve performance. The fundamental idea behind interpreting these images is about understanding what can cause splice loss. In the images, there are certain image artifacts to look for. These artifacts point to either some sort of pre-splice fiber-related variable or to some sort of splice mode-related variation. Most of the time, there is a combination of the two, but in many cases, one effect or another will tend to dominate the image. In general, loss arises from either a fiber-related condition or a splice mode condition. Fiber-related conditions are things about the fiber that are either intrinsic to the fiber itself or come about from variations in fiber preparation technique. This includes factors such as cladding diameter tolerance, node field diameter variation, core cladding concentricity error, glass chemistry, cleave angle, cleave shape, etc. The key here is that these are all aspects of the fiber itself that need to be handled by the splice mode. For example, cleave angles can be handled by setting the cleave angle alarm threshold properly to reject large angles, or perhaps the glass chemistry of an active fiber requires a lower arc power to prevent excessive dopant diffusion during the splice. In the splice images, the main fiber-related conditions commonly observed are from splices with a cladding offset, a core offset, splices with a large fiber angle, mode field diameter mismatch, or splices with a large cleave angle. Each one of these has a unique presentation, but on a high level, here are some quick diagnoses for each of these. When fibers are spliced with a cladding offset, usually you'll see some core deformation or core smearing at the splice point. Correct this by experimenting with the eccentricity correction function, or ECF value, to minimize core deformation at the splice. When fibers with poor core cladding concentricity are spliced with cladding alignment, you're very likely to see a core offset. This can be corrected by changing the XY alignment method to use core alignment instead of cladding alignment. Note that this only applies to fibers where the core is visible. Polarization maintaining fibers and others like it are not compatible with XY core alignment. When fibers are spliced with a large fiber axis angle, you'll tend to see core macro bending. To correct this, ensure either the cladding only or the coating only rests in the V-grooves. Also ensure the grooves and the fiber are properly cleaned. When fibers having dissimilar mode field diameters are spliced together, there is a certain amount of baseline loss that comes from the dissimilarity. This mode field mismatch can be mitigated to some extent by extending the arc power or the arc time. Another option for very sensitive fibers is to explore the idea of changing the gap set position so that the smaller mode field diameter fiber is heated more than the larger. This promotes diffusion of the core dopants into the fiber's cladding, thereby expanding the mode field of the smaller fiber to more closely match the larger mode field diameter of the other fiber. When fibers with large cleave angles are spliced, you're likely to see some microbending of the core. This can be mitigated by either using a longer prefuse and main arc time, or by tightening the cleave angle alarm threshold in the splice mode. So now that we've gone over the fiber-related conditions, a splice mode condition, on the other hand, refers to a parameter in the splice mode or a physical aspect of the splicer that could be affecting the splice. For example, maybe the electrodes are worn, causing an erratic arc discharge, or maybe a setting is not tuned properly, leading to poor splice performance. Like the fiber-related conditions, the splice mode parameters can produce some unique image features as well. These are mostly tied to the heating phase of the splice, however, meaning that the arc and the overlap are really the main factors in play. For example, if you see the rippling effect in the core, it's an indication of excessive overlap or insufficient prefuse time and power. Similarly, if you see the core losing definition at the splice point, it's an indication of too much arc power or too much arc time. To the trained eye, the splice images can provide clues pointing to what could have been the cause of splice loss. This is especially important and helpful during splice optimization, as these are all direct clues to unlocking the ideal parameter set. Think of it like a high-level map. It won't tell you the exact location you need to go, but it'll let you know the general vicinity of where you're heading, so you can go in the right direction and follow the signs along the way. So now that the optimization procedure is wrapping up, you will have ideally arrived at a set of parameters that provide a splice which meets the performance criteria for your unique application. Up until now, we've touched on loss estimation, but have been primarily focused on loss measurement. The real-time measurement has been the vehicle for deciding which parameters we should change in order to improve splice quality. And indeed, loss measurement is a critical part of splice optimization. However, it's not always practical to verify the splice performance using the actual measured loss of the splice every time. We can use the splicer's ability to analyze the splice image artifacts as a way to get an accurate estimation of what the splice's performance would be. As we start tuning the splice loss estimation, we'll first decide between using the splicer's old method or the new method. The old method utilizes core step, core curve, and mode field diameter mismatch as the parameters for adjusting loss sensitivity. This method is generally good for observing butt splices or splices characterized by little core deformation, such as splices with a low arc power or splices using cladding alignment, like multimode or coreless fiber splices. The old method doesn't directly account for wavelength, so it can be used accurately in some cases, but won't always provide the best results with normal fusion splices or with more unique splices. In contrast to the old method, the new method combines all of the old method observations with the theory that splice loss arises from microdeformations or microbends at the splice point. This means loss estimation calculations are based on the idea that for the portion of the fibers within the heating zone, a fundamental core deformation function can detect any deviation from the normal core image and interpret the results. The new loss estimation method incorporates the wavelength as an additional factor of the core deformation calculation, allowing it to be a much more powerful method for estimating splice loss. While both the old and the new method are fundamentally different, they both account for the difference in mode field diameter between fibers. Since MFD represents the true light-carrying region of the fiber, a mismatch between fibers here will tend to result in higher splice loss. Splices like this do tend to carry some baseline level of intrinsic loss and are more difficult to optimize. Many times, a splice with dissimilar MFDs benefits from a very long arc time. But there are many other ways to approach mode field transitions, especially when the difference is very great. In some cases, it may be helpful to have a specialized mode field adapter component for matching the mode fields. So after getting the splice mode parameters tuned in the best I can, I'll open the loss estimation tab to begin optimizing the estimation parameters to most closely match my measured loss values. To do this, I'll load in the data that was collected during the optimization process and begin adjusting the modifiers until the estimated loss values and the measured loss values most closely overlap. During the estimation tuning process, it's important to include both the high loss and the low loss splices to capture the best possible statistical significance for the dataset. This ensures your estimation truly captures the splice's performance. The estimation tolerance window is shown by the diagonal red and green bars, indicating the deviation from what would be considered a perfect one-to-one match. To change the allowance window size, I can adjust the maximum allowable difference setting to either a broader or narrower tolerance deviation of the estimated loss from the measured loss. Once my window size is set and I've identified my window of tolerance, I'll use the parameters in the modifiers section to adjust the dataset. The MFD mismatch sensitivity and MFD mismatch offset modifiers will adjust different aspects of measuring mode field mismatch. These can have different effects based on the way the images present, but they both modify the way the splicer calculates the portion of splice loss due to mode field mismatch. The core deformation modifier pays close attention to the exact splice point, looking for image artifacts that indicate different sources of splice loss. Depending on the fiber, adjustments to this parameter can have quite varied effects on the final layout of the data, but don't be afraid to plug in different values and observe how the data changes in response. The last FPS tool in your estimation tuning tool belt is the minimum loss parameter. On the graph, this applies a vertical offset to each data point. If there's always going to be a baseline amount of loss in the splice, this is where it should be accounted. The fundamental idea is that these parameters are supposed to be adjusted until you see the best fit behavior. So again, don't hesitate to spend some time sweeping through the different value ranges and experimenting with what the data looks like. Finally, after optimizing all of the splice mode parameters and tuning the estimation settings in FPS, transfer the estimation modifier values to the requisite setting fields in the splice mode itself. It's ideal to verify the optimized recipe with a few different splicers, performing a predetermined number of splices per unit. Generally, 30 splices is enough for an effective data set, but more data can be collected if desired. Optimizing a splice mode can seem like it's tedious and overwhelming. And without a framework, it most definitely is both tedious and overwhelming. With the right tools and techniques, however, the mountain of what-ifs can be cut down to a few key considerations, where, when paired with experience and some splicing intuition, can get you to a good working splice recipe in no time at all.